Thank you very much for the kind introduction. And yeah, so it's 11:30 in Japan, so I'm a bit my brain is a bit slow, but let me start. And firstly, I would like to thank the organizers of this symposium for giving me opportunity to give a for me to have a presentation here. So today I'm going to talk about our recent efforts on HHG in stronger equality systems. Mhm. Mhm. Okay, so here's a table of the contents of today's talk. So first, I would like to give a brief introduction of non-quantum physics in stronger equality systems, and also HHG physics. And then we discuss some basic feature and picture of HHG in Mott insulators, and also discuss the important role of spin charge coupling in HHG in Mott insulators. So let's start. The combination of strong light and some material usually allows us to control their physical properties. So for example, in the case of controlling of material properties, a prominent example includes photo-induced phase transition, photodoping effect, Flocken engineering, and nonlinear phonics, and so on. On the other hand, when we view the things from the optical response, prominent example includes high-harmonic generation, shift current, Higgs spectroscopy in superconductors, and so on. And this kind of new concepts and physics are recently actively explored because of the recent development of strong laser techniques in the terahertz and the mid-infrared regimes. And exploration of such non-quantum physics would be very important, technologically important, like an application for the photoelectronics, quantum technology, and potential new spectroscopic applications. And when we explore this kind of non-quantum physics, we think that the one particular interesting playground is stronger equality systems. So as we know, in these systems, electronic correlation plays crucial role, and this leads to correlation between different degrees of freedom, like charge, spin, orbit, and phonons. And because of the detailed balance between these degrees of freedom, there emerges a collective phenomena in and out of equilibrium. So in equilibrium, so this kind of situation is nicely exemplified, for example, in couplets, which provides very rich physics and various orders. And if we imagine to excite this stronger equal systems with some lasers, we can expect that there would be some intriguing optical response emerging out of elementary excitations coming from strong correlations. And we can also tune the detailed balance between different degrees of freedom with the light. So therefore, we can naturally expect some rich photo-induced phase transitions. And recently, if you are interested in this kind of topics, in particular in the Mott insulators systems, I would like to invite you to see some recent review on this topic. But today, actually, although there are many topics, today I would like to focus on the one particular example, which is high-harmonic generation. So HHG is a nonlinear optical phenomena where you obtain a higher harmonic component of injected light to some material. So it was originally observed in atomic gas systems, and it is technologically important and has been used for laser frequency conversions and attosecond pulse generations. So when you look at the HHG intensity, you typically see this kind of structure, including some plateaus, which indicates the non-perturbative nature of this phenomena. The basic physics is understood by the so-called three-step model, which describes the dynamics of an electron in atomic potential. More recently, the scope of HHG research has been extended to condensed matters, in particular semiconductors. Due to the periodic potential coming from atoms, the dynamics of charge would be different from gas systems. So therefore, people expect different HHG properties compared to the gas systems. So the origin of HHG in semiconductor is considered to be coming from mainly two mechanisms. The first one is so-called intraband mechanism, where the laser create charge carriers, and these charge carrier move around, staying in the band to contribute the current and also to the emissions. And the second mechanism is so-called the interband mechanism, where electron hole pair is created. They move around, and at some point it comes back to the same place to recombine to emit the kinetic energy acquired till then. So in any case, these scenarios are highly related to the information of the band structure in semiconductors. So people try to use this HHG as a spectroscopic tool for the band information in semiconductors. So actually in this field, people witnessed a huge excitement of HHG research in semiconductors. So one of the big reasons here is that the combination of strong light and characteristic concepts in semiconductors allow us to explore new physics beyond atomic gas systems, and also open new possibility of spectroscopy. And in this talk, instead of semiconductors, I would like to shed a light on another important class of material, which is strongly correlated systems. So because we also have various characteristic concepts unique to strongly correlated systems, we expect that the combination with a strong light provides some playground to explore new physics beyond semiconductors, and also some possibility of new spectroscopic application of HHG. And to challenge this kind of question, what we did is to first focus on fundamental model of a strongly correlated system, which is a Hamilton. So the Hamiltonian is shown here, and the effect of the electric field is considered through the pious phase. And in equilibrium at half filling, when the Coulomb interaction is large compared to the hopping, electron cannot move from this kind of singly occupied configuration, and the system becomes an Mott insulator. So now we consider to excite this system with some lasers, and usually we get some non-occupied side holon and the doubly occupied side doublons, and they are the basic charge carriers of this system. So now the question is, what is the mechanism of HHG in Mott insulators, and what is the physics absent in semiconductors? So in order to deal with the non-equilibrium problem of the strongly correlated systems, we used two complementary tools. So one is the non-equilibrium extension of dynamical mean field theory, which is applicable to the high-dimensional systems. So actually, a non-equilibrium DMFT have two variants. One is the so-called Floquet DMFT, which directly access the time periodic steady state. And the other is real-time DMFT, which start from some equilibrium state and see the time evolution from there. And the second method is so-called ITEBD, based on the tensor network, and we can directly access the thermodynamic limit, and it's applicable to the low-dimensional systems. So we implement this method using some open library, and so iTensor is developed in CCQ. So as a parameter, we use this kind of parameters. So in short, we consider the Mott system with a well-defined gap, and consider the subgap excitation like this. So if you have couplets in your mind, our theory unit roughly corresponds to 0.5 electron volt, so which means that we are exciting the system with mid-infrared lasers. And we evaluate the HHG spectrum from the photo-induced current shown here. So now we would like to discuss the basic picture and the feature of HHG in Mott insulators. So here's the result of the HHG spectrum obtained from the Floquet DMFT. So you can see that the structure of a spectrum qualitatively different between the weaker field regime and the stronger field regime. So in the weaker field regime, we see a single plateau structure here. But if we go to stronger field regime, you start to see multiple plateau-like structures. So first question we would like to address is, what is the origin of the HHG process? So as we have two different processes in the case of semiconductors, even also for the Mott insulators, we can think of two different processes. So one is doublon-holon hopping process, where the number of doublon and holon do not change, but contribute to the current. And the second one is doublon-holon recombination process like this, which is analogous to the interband current in the case of semiconductors. So we can numerically calculate or separate these two contributions, and we can find that actually in both regimes, doublon-holon recombination is a dominant process. So here I show the summary of the HHG intensity in the plane of frequency and the field strength. And you can also see this cutoff of the plateau. So here what we can see that in both regimes, the cutoff scales linearly against the electric field, but the cutoff, the coefficient is different. In particular, in the stronger field regime, cutoff scales with this simple formula, which is like U plus integer times electric field. So these different behavior in two regimes can be connected by the change in the qualitative change in the dynamics of doublon and holons. So to get the hint, here we calculated the time average density of state under the periodic field. And you can see that in the stronger field regime, you start to see some side peaks develops from the main Hubbard bands. So actually, these side peaks corresponds to the formation of the so-called one-year stack ladders, which indicates the localization of the charge carriers. So from this, we can get the following two scenarios. So in the stronger field regime, first doublon-holon pair is created, but because of the strong field, they are localized. So, but at some point, this localized pair gets recombined to emit the light. But because of this localization, the mth neighbor light pairs give some emission like a U plus M times E. So this explains the formation of the M plateau structures. On the other hand, in the weaker field regime, after the doublon-holon pair is created, they are itinerant, and they can acquire kinetic energy, and there is an emission of the kinetic energy. So now we consider the relation between HHG and the single particle spectrum in detail. So note that they are closely related in the case of semiconductors. So here is a single particle spectrum from the dynamical main field theory, and the upper Hubbard band and the lower Hubbard band looks parallel to each other. So this dispersion resembles the case of indirect gap semiconductors. So what we did here is to construct an effective semiconductor model like this, which resembles the dynamics of charge in the Hubbard model. And we show the corresponding dispersion here, these white dashed lines. And we compare the resultant HHG for the Mott insulator and this semiconductor. And you can see that they don't match to each other. On the other hand, if we forget about the single particle dispersion, and be brave enough to change its dispersion to this orange one, like a direct gap semiconductors. Now we can see that this HHG spectrum of this model qualitatively match with the Mott insulator, although the single particle spectrum is very different. So this comparison suggests that the HHG in Mott insulator is not directly reflecting a single particle spectrum, unlike semiconductors. So now the question is, what information actually we are looking through the high harmonic generation? So to discuss in detail, we decided to look at the one-dimensional systems. So here's a HHG spectrum for the one-dimensional Harvard model obtained from the ITEBD simulation. So the basic feature of HHG is essentially same as DMFT. So namely, the cutoff scales linearly against the electric field, and the dominant doublon-holon recombination is a dominant process. So now we consider the relation between HHG and the elementary excitation. So in 1D Harvard model, there exist well-defined elementary excitations called spin-on, holon, and doublon. So in particular, one electron can be regarded as a combination of spin-on and doublon. The physical picture is like this. So when you have add one electron to the system, so you have initially this configuration, but as time evolves, it's split into 2 degrees of freedom. One is spin-on, one is kink in the spin background, and the other is doubly occupied site, and they can move independently. So form is spin-on, and the latter is doublon. And from the beta-ansatz solution, we know we can know the precise dispersion of these elementary excitations. And for the doublon and the holon, we have this kind of bit complicated expression. So now the question is how this information of elementary excitations are related to HHG. So this can be this point can be discussed using the so-called semi-classical 3-step model. So it was originally developed in the gas systems and later on extended to semiconductors to discuss the HHG physics in these materials. And the important point is that the electron acquire momentum shift under the vector under the electric field. And semiconductor 3-step model is explained as follows. At some point T0, an electron hole pair is created by the tunneling at the gap minimum and especially at the same place. And after that, they move around following this kinetic equation determined by the dispersion of the electron at the conduction band and the valence band. And at some point, it comes back to the same place to recombine and emit the light, corresponding to the kinetic energy. On the other hand, in the case of Mott insulators, actually this doublon and the holons are also charged elementary excitations, and they acquire momentum shift under the electric field. So this point has been discussed in the context of the electric breakdown of Mott insulators. So naively speaking, we would expect that if we replace this electron hole pair information to this doublon holon pair information obtained from the many body theory, we may use this 3-step model to describe the HHG process in the Mott insulators. So this point can be checked by so-called sub-cycle analysis. So namely, what we do is to make a window Fourier transform of the current around some time Tp, and then get some temporal radiation spectrum around that time. So here's the result, and you can see this change in the temporal radiation, but this behavior is now explained by the semi-classical 3-step model combined with the information of the doublon holon pairs. So this is nice because it tells that this 3-step picture can be widely used even for strongly correlated systems as far as we use proper information of charged elementary excitations. And so therefore HHG may be used as a probe for the many body states in a strongly correlated system if we look at HHG of these systems. And so these are the basic pictures, but now we would like to discuss the important role of spin charge couplings, which is characteristic in Mott insulators. So in Mott insulators, the spin exchange interaction tends to make spin configuration antiferromagnetic. So when charge carriers are added like this, and they move around, their dynamics inevitably disturb the spin background, and it can break some antiferromagnetic correlations at the energy cost of exchange energy. So this kind of intertwined motion of charge and spin background is the origin of spin charge coupling in Mott insulators. And we recently found that this kind of spin charge coupling have a multi-phased effects on HHG. And one of the big reasons that we pursue this spin charge coupling effect on HHG is coming from some experiment of HHG in calcium ruthenium O4. So this material, when they decrease the temperature, the Mott gap is substantially enhanced. And in this experiment, by applying the subgap excitation, they found that this HHG intensity increases almost exponentially as a function of this Mott gap. And this kind of behavior is not seen in conventional semiconductor like indium arsenide. And they also found some peculiar scaling about this increase ratio, which turns out to be independent of the excitation frequency. So this is a rather strange behavior. And so we would like to understand whether what is the origin, in particular, what is the role of many body effects, and whether the Harvard model already includes this physics. So what we apply the dynamical mean field theory to the Harvard model. So first, let's look at the equilibrium properties. So in this system, we have antiferromagnetic ground state at low temperatures. And if you look at the density of state, the Mott gap gradually increases with decreasing the temperature. And at the same time, you start to see multiple peaks in the Hubbard bands, which indicates the formation of a spin polaron due to the strong spin charge coupling in this system. We again note that this doublon-holon dynamics is accompanied by the disturbance of the spin background at the cost of exchange energy, which suggests the energy exchange between the doublon-holon kinetic energy and the spin background energy. Now, if we look at this density of state and expect what happens for the subgap for the HHG for the subgap excitation, we may naively expect that HHG may be suppressed under the low temperature at the low temperatures, because now we expect less photogeneration of carriers. So indeed, if we count the number of photocarriers after the field, there is a substantial decrease, as can be seen by the occupation number of the upper Hubbard band after the pulse. On the other hand, if you look at the HHG intensity, there is a strong enhancement as lowering the temperature. And if you look this as a function of the Mott gap, the enhancement looks almost linear, exponentially as a function of the Mott gap. So this part is qualitatively same as the experiment on calcium ruthenium O4. So now we want to review the origin of this peculiar behavior. So to get a hint, we first make a subcycle analysis. The first is for the high temperature phase and the second is for the low temperature phase. And the red and blue lines are the trajectory of the doublon-holon pair extracted from these results. So firstly, one realized that the weight of its weight is concentrated on early stage of the one cycle of the field, even at low temperatures. So this suggests a short coherence time of the doublon-holon pair. So secondly, one finds that trajectory of doublon-holon pairs are almost same for these two cases, and the difference is mainly explained by the gap change, gap difference. So the major difference between these two cases is actually the coherence time of the doublon-holon pairs. So in addition, by changing the by changing the interaction size U, the difference between high temperature state and low temperature state is gradually lifted, as shown here. Yeah, and for large U, exchange energy gets smaller, and therefore we expect a small energy exchange between doublon-holon kinetic energy and the spin background. So this analysis suggests the following scenario of strong enhancement of HHG. So although the number of the carriers are substantially suppressed by the gap enhancement, the drastic change in the coherence time originating from strong spin charge coupling dominates the former effect and end up with a strong enhancement of HHG. So to clarify the role of spin charge coupling and to support the scenario, we compare the case with and without spin charge coupling. So this can be done by considering one-dimensional system with a staggered magnetic field. And without field, we have spin charge separation. But with staggered field, doublon-holon dynamics always make some mismatch between the spin configuration and this applied field, as in the case of a high-dimensional system. So therefore, one can emulate some part of spin charge coupling with this model. So if you look at the result of the sub-cycle analysis, it looks like this. So without spin charge coupling, the main weight is located for the doublon-holon pair with a long time interval between its creation and annihilation. But with the spin charge coupling, the weight is shifted for the short-lived doublon-holon pairs. So this indicates that the coherence time of the doublon-holon pair are efficiently suppressed by the spin charge coupling, and it is consistent with the result of DMFT at low temperatures. So further reduction of coherence of doublon-holon pair with increasing the temperature can be explained as a combination of spin charge coupling and the thermal fluctuations. So remember that at finite temperature, the observed quantity is the average one for different initial state as described by the density matrix. So in the present case, we need to consider the contribution coming from different spin configurations. However, the dynamics of doublon and holon would be different for each configuration since the energy transfer between the doublon-holon kinetic energy and the spin background would be different during the excursion. And it should depend on the spin configuration. So this naturally, therefore, this kind of difference would naturally lead to a dephasing of the current for different initial state and make the coherence time of the doublon-holon pair smaller after the thermal average of these contributions. So to support this, here we calculated how the phase of current at the given frequency changes with the staggered field, which mimics difference between different spin configurations. And one can see that there is a very strong dependence of the phase, and these results support the above-mentioned scenario. So we note that the difference between different spin configuration should be lifted when the exchange energy becomes smaller. And this explains the observation in DMFT that until the difference between low temperature and the high temperature state is lifted for large use cases. And I would like to briefly touch the phenomenological scaling law. So in the experiment, they observe this scaling when they look at the above gap behavior. And actually, even for the Harvard model calculation, if we just look at the above gap regime, we can see that this scaling almost fit the result. And it also reproduces the independence of the increase ratio against the excitation frequency. But we still don't know what is the origin behind this. And so with this analysis, we found that the strong spin charge coupling leads to intrinsically short coherence time, as well as a strong temperature dependence. And so they lead to a peculiar, and this combination leads to a peculiar temperature dependence on HHG in Mott insulator, as has been reported on calcium ruthenium 4. And another message here is that the spin charge coupling, of course, depends on the dimensionality in Mott insulators. So actually, in Mott insulator, the dimensionality should play a crucial role on HHG in Mott insulators. And therefore, I would expect that it would be very interesting to study the dimensional crossover of HHG using some material like this, which covers the 1D and 2-dimensional system. And actually, we recently operated some IT-EBT simulation for the 2-regulator system and found that there is even richer physics, HHG physics, coming from the spin charge couplings. But it seems, okay, so just 3 more minutes. And so I don't go in detail because we don't have time, but just let me just flash the result of this analysis. So what we did is to study the HHG in 2-regulator system as a function of hopping along the chain. And so here I show the Ty equal to 0 result, and but you can see some peaks, but it's located at even harmonics. So this is a bit strange because the inversion symmetry of this system predict the high harmonic spectrum at the odd harmonics usually. And as we increase it to Ty to 0.5, the peak is now shifted to expected odd harmonics. And if we make it even strong, Ty stronger, we start to see multiple plateau like this. Yeah, 2 plateau like this. And the same for the Ty equal to 1.5. So in short, there is a substantial change in the qualitative feature of HHG in 2-regulator system as a function of Ty. And this kind of change is not expected in the case of semiconductors. So actually, this drastic change is attributed to spin charge coupling, but with a different effects. So here I summarize just the key findings here. So one unique effect we found is that is the unique dephasing mechanism originating from the existence of non-local spin charge coupling. And the second important process we found is that there is a fractionalized HHG processes that represent the dynamics of the doublon holon pairs and also spin polaron pairs at the same time. But yeah, sorry, I could not go in detail, but yeah, these are coming from the spin charge coupling, the different aspect of spin charge couplings. Yes, sorry, and then I would like to summarize my talk. So in this talk, we explore the interesting physics of HHG in a stronger quality system using the Harvard model as a test bed. And we pointed out the importance of the 3-step picture but it should be combined with the proper information of charged elementary excitations. And we also discussed the important role of spin charge couplings. And so I think this combination of strong light and strong correlation is a very interesting question, and it allows us to explore new physics in various directions. And even in the context of HHG, recently there are many efforts to explore interesting physics. And finally, I would like to acknowledge my great collaborators, and also would like to thank your attention.
Thank you very much, Yuta, for the nice talk.
Thank you.
We have 8 minutes for questions, so please raise your hand on Zoom. Andrew?
Hi. Hi, great
Hey.
talk. So I realize that this is a slightly ignorant question, or more than slightly, and it's partly answered by what you showed in the calcium ruthenate. But to what extent is the holon doublon picture really adequate in real materials? You know, in most cases, the upper Hubbard band is mixed up with other charge transfer bands. The low-lying excitation may be a charge transfer excitation. So
Yes.
How is this changed in real materials?
Yeah, so I think in real material, we need to change this doublon holon to proper elementary excitations. Yeah, so I think that's one thing. And the second thing is that, okay, so calcium ruthenate it is multi-orbital system. So I think not only the spin charge coupling plays a role, but actually there would be some role, the similar role would be played by this Hund's coupling or some orbital degrees of freedom. So basically, if you consider some electron move from one side to the other, there remains some some high spin states behind. It's like a chain. Antiferro. So it's like similar to chain structure of the antiferromagnetic dynamics of charge in the antiferromagnetic background. So, and I think this kind of spin charge orbit coupling would lead to dephasing, similar to what we discussed here. So although I'm limited, so my discussion is quite limited to the Harvard model, but I think we can get some insight or some that what is going on in a more general systems. And so I think this is the role of the Harvard model that we are looking at. So it gives some hint for the stronger core system, but I'm not saying that the same thing happens or exactly the same thing happens in other cases. But we need to properly replace what is what. So
yeah, but I guess my question was really what might be other physics in realistic situations? Because I thought that really to get higher harmonics, you wanted to make an excitation and then you needed it to kind of oscillate rapidly for a couple of oscillations. So you get, right? And the worry about most real materials is that it will just decay into something else because there's a lot of other stuff up there. So is it correct that the crucial thing we have to understand for real materials is the other decay channels?
I think so. Yeah, on top of these decay channels, there would be additional, and that would be also crucial. But yes, that's one thing. So compared to semiconductor, so there are two things. So in the correlated material, there's an additional channel. Compared to semiconductor, there's additional channel that contribute to the decay process. That's one thing. And it's spin charge coupling is one of the typical one, and that actually leads to unexpectedly large temperature dependence. So that is something people missed in the context of HHG research in semiconductors. But the second thing is that this kind of coupling can lead to emergence of new elementary excitations that gives additional unexpected dynamics of charge carriers. And this gives additional some feature in HHG. That is something that I wanted to explained in this part. Yeah. So for example, this first Plato here is coming from the spin polar, and that originates from this spin charge coupling and emergence of new elementary excitations.
Great. Thank you very much.
Yes, thank you for the question.
More questions? Okay, well,
sorry, then if we have 1 second, may I ask another question, not directly related to your talk? You explained beautifully how the HHG spectra reveal interesting and new physics in different contexts. Is there a technological advantage to using correlated materials instead of semiconductors?
Yeah, at this point, yeah, so there is not so much technological. I think one possibility is spectroscopic application. So I think there are two. So HHG have two roles. So one is really using it as a new laser source that gives a strong frequency, intensity laser. And I think after giving this kind of dephasing channel effect, I think discussing this dephasing strong dephasing effect on strong for the system, I think this kind of direction is not so promising. Although, if you look at 1D, it in history, it is known that in the one-dimensional Mott system, because of the peculiar structure of the excitation spectrum, there is a huge third harmonic generation. This is historically pointed out. So I think one possibility is considered one-dimensional system, but in the generic system, I think dephasing prohibits, disturb this strong HHG. But the other direction, but on the other hand, maybe it still have some HHG in correlated material have some potential in the spectroscopic applications. Yeah, so like detecting some hidden dispersion in the elementary excitation and so on. So maybe this latter direction would be more promising from my point of view.
Thank you very much.
Thank you.
Okay, let's thank Yuta again for the great talk.
Thank you very much.